All right, so we are going to be talking about circles and just identifying tangent, secants, and chords and using that to help us solve problems. So this photo that you see, oops, did not mean to draw that. This photograph was taken 216 miles above Earth. From this altitude, it is easy to see the curvature of the horizon, and facts about circles can help us understand details about Earth. So just a quick review. Recall that a circle is a set of all points on a plane that are equidistant from a given point called the center of a circle. And equidistant just means it's an equal distance. And it is from the center or to the center of the circle. And when we notate circle, or when we notate with a circle, we just have a little circle with a dot in the middle and the letter that is at the center of the circle. So the interior of a circle is a set of all points, inside of the circle. And the exterior of a circle is the set of all points outside of the circle. So getting into the vocabulary of the parts of a circle, the first one is a chord. And a chord is a segment whose endpoints lie on the circle. So if you notice with this chord over here, its endpoints are on the circle itself, so that's what makes it a chord. Chords can also go down the middle of the circle, off to the side, doesn't really matter as long as the endpoints are on the circle itself. A secant is a line, touched it with my hand, is a line that intersects a circle at 2 points. So if you notice with this secant, it intersects at those 2 points and it keeps going. The main part is that it's a line. With a chord, it's a segment. So there are going to be times where you have chords inside of secants, depending on what you're given, because we can't identify chords without having letters for that intersection. The next one is a tangent, is a line that is in the same plane as a circle and intersects at 1 point. So tangent. And then the point where the tangent and the circle intersect is called the point of tangency. Okay. So using those parts, we're going to identify the line or segment that intersects circle L. So starting with chords, we're looking for endpoints on the circle. And so for me, I see that this one touches and touches. So we have KM. And then we also have JM. And even though it's a line, when you just have a straight line, you're saying line segment JM. So it is a chord. When we get into secant, it's also going to be JM, but now we need to recognize the fact that it is a line. So to do that, you just write JM, and you draw little arrows on the end of the line you put above it. For diameter, it is going to be KM again, because it goes through the center. And again, we have just the straight line. With tangent, we have line M, which is this line right here. And sometimes with lines, we will identify it with just a cursive single letter, or sometimes you may have to use 2 letters to describe it, depending on what you're given. Our point of tangency is at H, even though I did not draw it, it is at letter H. And then radii is just the plural of radius. So if you look at this drawing, we have KL as a radius, ML as a radius, and JL. Okay, and again, radius just goes from the center of the circle out. Okay, so our next one, looking at circle P now, chords, we have QR. And by the way, feel free to pause the video if you're trying to do this real fast. But we have QR, and then we also have TS. And again, it's just line segment TS because TS is also a line. So for secant, it's also TS. So remember to show that it is a line, you just put little arrows on the end. And then for diameter, guess what? It's also TS. But again, it's line segment TS. For our tangent line, we have two letters. So rather than then saying, oh, well, this is L, now we just have two letters. So it's going to be line UV. So again, if it's the line, make sure you're using the line symbol above. Our point of tangency would be at U. And then our radii, we would have QP, TP, and SP. Okay. So looking at these next ones, we have two circles that have the exact same radii. And when you have the same radius between two circles, the circles are just congruent circles. And then if you have two circles that are right on top of each other and they share the center, kind of like right here, the blue and the red circles share that center, those are called concentric circles. My E and N, but kind of funky. There we go. So concentric is when they share that center piece. And then our last one, if we have two circles that meet at a single point, they are called tangent circles. Okay. So looking at this, we want to just identify some major points of these circles. So if I need the radius of S, I'm looking at circle S, which is the smaller one, and you're just going to count. I have 1.5. So my radius is 1.5. For radius of R, again, we're counting. I have 1 and 2. So my radius is 2. And you can go up or left or down. It doesn't really matter. Our point of tangency is going to be the ordered pair where they hit, which would be at -2, 0. And then our equation of a tangent line, because it has to be tangent, I know it has to be horizontal. And for horizontal lines, it's always going to be y equals something. So in this case, it'll be y equals 0 because it should be the same as that one. And just a quick thing with vertical and horizontal. When you have a vertical line like I drew, or sorry, a horizontal line like I drew, on that line, the only value that does not change is y, because y is always equal to 0. So anytime you want a horizontal line, it's always going to be y equals some number. When you get into vertical lines, the only thing that doesn't change is your x values. So your vertical line will be x equals something. And this will come into play later when you have other examples. So moving on from there. Oh, and another thing with this, just make sure that your whatever your tangent line is equal to, make sure that it's one of the numbers from your point of tangency, because it should be matching that in order to actually be the tangent line. So our next one, a common tangent, is a line that is tangent to two circles. So this one on the left is actually external tangents because they're on the outside of the circle, lines L and M. This blue one are internal tangents because they're going towards that center, lines P and Q. So for these theorems, you do not have to know the theorem numbers or anything like that. I'll fill them in just in case you want them because they do match up with the theorem numbers in your book. But all this theorem is saying is that when you have a line that you know is tangent to the circle, then you know that that line is also perpendicular to the radius drawn to your point of tangency. So here, my point of tangency is B. So when I draw my radius from A to B, I know it is perpendicular to line L. So line L, conclusion, is perpendicular to line segment AB. There we go. So then for our next one, it is 12-1-2. And this one is just kind of the opposite. If you are given a line drawn against a circle and you see this little 90 degree with the radius that they drew, then you know that M is tangent to CD or to circle D. Okay, so it's just the opposite. If you're given the radius to the line is 90 degrees and you know that that line is tangent, or if you go back up to 12-1-1, if you are given a line that you know is tangent, then you know it makes a 90-degree angle. So this is going to be handy when we do this problem. So early in its flight, the Apollo 11 spacecraft orbited Earth at an altitude of 120 miles. What is the distance from the spacecraft to the Earth's horizon rounded to the nearest mile? Draw and label a diagram to support your answer. And just FYI, it is 4,000 miles from the center of the Earth to the surface, which is our radius. So in order to draw a picture, first off, we need Earth. So here's Earth. So with this Earth, we know it is 4,000 miles to the top. But this Apollo 11 spacecraft went above the Earth. So that means I'm going to, oh goodness, it's not working. So I went above the Earth 120 miles. Now, because we are looking from the spacecraft, if you are looking at the horizon, you are seeing your farthest point that you can see on the planet, which means that that's actually your tangent. Because if we were up in the spacecraft at the top of my little orange line and I'm looking at the Earth, as I draw it, where my line touches Earth would be my horizon, which is also going to just be tangent. So because that line can be formed, I'm just going to call that X. And then going back to the Earth to that point of tangency is also going to be 4,000 miles. But on top of that, going back to the theorem we just had, because I have a line that I know is tangent, I also know that it's going to be a 90-degree angle. So with this, I have a 90-degree angle. And now it looks like a Pythagorean theorem problem because we have a right triangle and two sides that we know and one that we don't. So in order to set this up, we would have a squared plus b squared equals c squared. A squared, I'm going to call 4,000. B squared is going to just be the x squared because it's another leg. And c squared should always be your hypotenuse. And if you are the type that it's easier for you to identify what this is before you plug it in, that's fine. The total length is 4,120, so I plug in 4,120 squared. So then, when you do this, we will subtract 4,000 squared, and the reason why I am not giving you the actual number is because it's humongous, but we would have x squared equals, now the difference between these, when you actually do 4,120 squared minus 4,000 squared, is 974,400. So then, when we take the square root, we get that x is approximately 987.11 miles. But because, again, we wanted nearest mile, it'd be 987 miles. So what this means is if you were actually on the Apollo 11, wherever it was in space, you would actually be able to see 987 miles to the curvature of the Earth, which is pretty cool. So now we're going to do it again, except with a mountain, and you could actually do this again with Pikes Peak if you want. So Kilimanjaro, the tallest mountain in Africa, is 19,340 feet tall. What is the distance from the summit of Kilimanjaro to the horizon to the nearest mile? Draw and label a diagram to support your answer. And if you didn't notice, the height of Kilimanjaro was in feet, and I need it in miles. So we need to convert, and there is our conversion. So in order to convert, we have 19,340 miles, and we're going to, feet, not miles. Whew. And we are going to divide it by 5,280 miles. And when we do that, we get that the height is approximately 3.66. And this would be miles. So then, we are going to draw our picture. So we have Earth. We have our radius. Whenever you have a problem that talks about how far it is off of Earth and you need the measurement, just always use 4,000. But then this mountain goes up 3.66 miles. And then we're going to look at the horizon. And when I do that, boop, I know that this makes a 90-degree angle. So, and again, I know that my radius is 4,000. So then, to set it up, we would have 4,000 squared plus x squared equals 4,003.66 squared. Then when you subtract 4,000 squared, you end up getting that x squared equals 29,316.457. So when we take the square root, we would have x equals 171.22. So then nearest mile again is going to be 171 miles. So from the top of Kilimanjaro, you can actually see out 171 miles to the horizon. So, last little theorem we have, if you want the number, it is 12-1-3. But this theorem says that if you have two segments that are tangent to the circle and they have the same external point, kind of like you see in the picture, then the segments are congruent. So you can add little congruent symbols if you want, but because these lines are tangent and they meet at A, we know that AB is congruent to AC. So the main benefit to that is solving problems like this when we have two tangents that are meeting at R. So because I know that these should be the same, I'm just going to set them equal to each other. So then to cancel out this 4, we're going to multiply both sides by 4. So they cancel and we get x equals 4 times x is 4x. 4 times negative 6.3 is negative 25.2 or minus 25.2. Then, me personally, I would subtract 4x so that I can combine them, and it'll help me save some steps later. So this would be negative 3x equals negative 25.2. And then we divide by negative 3, and x equals 8.4. But before you all do your happy dance, remember, we're looking for RS. So we're going to have to plug in this 8.4 into RS. And RS equals x over 4, which means it's 8.4 divided by 4, which ends up being 2.1. And if you had chosen to plug it into RT and done 8.4 minus 6.3, you would still get 2.1, so it won't matter. Your homework is in the book again, but just a quick note with numbers 26 and number 27. You are going to have to use the formula 180 times n minus 2, and n is your number of sides.